Also on rather general topic, proper quotients of torus action.
Yeah, thank you very much. Yeah, maybe first because on this occasion it doesn't happen so often, but I would like to thank the organizers, Luis and Thomas, for inviting me, but for not giving up in organizing this wonderful conference. And thanks a lot. And instead of starting with reminiscence, I just wanted to thank Oscar. Congratulations and a big thank you for many more things that would fit on this recorded talk. But if I have to choose one, maybe it's for being such. I mean, you read a lot about energy crisis in the newspapers, and I mean, you're such a wonderful source of energy. That's kind of amazing. Thanks. Okay, so, and another thing is that he's also very patient with me when it comes to writing up things. And so this talk is also an excuse. I mean, it's also something I haven't written up yet, but it's also an excuse to tell you about things I've been thinking about while also thinking about things we were collaborating on. So, yeah, so I want to talk about proper quotients for torus actions. And maybe to give you some background how this came about. So maybe before I start, I should say that this is hopefully going to be joint work with Yucheng Zhang, who just finished his thesis with me, and sort of this is supposed to be the first project we do after his thesis. And so what's my motivation? So in this conference, I mean, we often have been looking at moduli spaces, and for moduli spaces, we know that. So the background motivation is that we start with a moduli space, moduli problem, and well, by now, most of the time when we just write it down in the correct way, it's easy to see that it's an algebraic stack, but that's not sort of not for all situations. That's a sufficiently nice thing to look at, but sort of in order to get something that's really a variety or a geometric object, we try to pick an open subset that we would call semi-stable or stable points that actually admits a moduli space. And so I've been working a bit on we found criteria for an algebraic stack. So for this open substack, if and only if criteria for such an open sub problem of our moduli problem to admit a good moduli space. And so what's kind of bothering me was that there's very few methods on actually choosing on how to choose such open sub problems. And so the most famous one comes from GIT. You pick a line bundle on your moduli problem, and this gives you some stability condition, and then you're happy you find your moduli space, hopefully. But there are some situations where we know that picking line bundles doesn't give you all possible choices. And there's others, and they are sporadic, and I would like to understand them better. And so one of these examples is the thing I wanted to talk about. So today is a very simple, in some sense, toy case where there was a conjecture on how to find all of these. And so this is a classical problem. So it's what is this set? So I take a torus, an algebraic torus. And sorry, so I'm in Madrid, so I should probably just say C star to the R. Acting on, no, but this is also something that's great about Oscar, that he doesn't mind if we talk in different languages, right? So I want to let it act on a projective variety. And a smooth projective variety. And so the moduli problem will not be a real moduli problem, but it will be what I would call the quotient stack. So that will be my M for today. And if you don't like stacks, so that doesn't matter. So but I want to look at open substacks that admit, say, a geometric quotient. A geometric quotient that is supposed to be proper again, because I don't want to have, I mean, as Vistoli says, I mean, working with non-compact moduli spaces like keeping your cash in a pocket with holes, so you cannot. That's all right. So you want a proper good moduli space, and sort of this has been classically formulated. I mean, there is nothing you need to know about stacks. You want to find open T invariant subsets that emit a geometric proper quotient. So there's this problem. So there's this conjecture of Bielinski-Birula, and Sumese, and I think it's from maybe 86 or something. I will explain it in a bit, characterizing all open T invariant U and X such that U mod T admits a proper geometric quotient. And so this was an interesting example for me, because in this case, you can easily, it's not hard to see that if you start out with any toric variety, you can obtain it in this way from such a datum. And because there's toric varieties that are proper but not projective, it will be impossible to construct these by choosing GIT line bundles. And so this is an example where you know a priori that you get more options than just from GIT. And this I found interesting. And so it seemed to be a natural problem to think about. And yeah, so what I want to do today is to remind you of what this conjecture is, give you the construction, and then tell you on how looking at it from this point of view gives you a way to understand the conjecture, to understand why it's true. And I should warn you, so I'm cheating slightly for this talk. So they actually have several versions of this. So they not only have for geometric quotients, but also for good quotients. And they there's lots of variants. So for example, there's a Kähler version instead of a projective version. And I'm not very good at Kähler geometry, but I had the impression that the Kähler version would be okay as well. I will use some geometric properties of the algebraic varieties with the torus action, but their theorems of order, all theorems give you the analog thing for Kähler varieties. So that seems to be okay. And in their original paper, they also weakened the smoothness to normal. My suspicion is that they did it because they were aiming for an inductive proof. And then you only know that these quotients by a one-dimensional torus will be normal, and then it's convenient to have this normal. And I haven't really thought about the normal situation that's not smooth. But that's what I want to explain, how to think about it. And so all examples that I will give you is kind of toy examples to think about. So so let me start by a reminder. So basic. So I want to recall this conjecture, and so I have to give you basic properties of basic geometric properties. For these varieties of torus actions. So first of all, I mean, so I will, because I assumed my variety to be projective, because it's smooth, I know that I can always find an ample line bundle on which this torus action actually lives. So that you probably all know why. Yeah, right. So the point is that the pK variety of the smooth projective variety is an abelian variety, and so the torus will act on it, but it cannot act because it's an abelian variety. So that's why you can lift the action to the power of the line bundle. And I will make such a choice. But this line bundle, so this will imply properties that this torus action is well behaved. The line bundle will not in the end be used to construct these open subsets. So what's the basic properties? So the first thing that you know is probably you look at the fixed point sets. So the fixed points are actually smooth closed subvarieties. So this is the fixed points. So this decomposes in a disjoint union, finitely many, where the Fi are the irreducible closed subvarieties. So they're again smooth because we have a torus. And of course, maybe you know, so I will collect a lot of stupidities in the beginning, but just to fix your idea. So of course, the dimension of the Fi's can vary a lot in all kinds of directions. Yes, sorry. Yes, no. And please keep reminding me of this. So this is keeping. Yes. Okay, so of course, the dimension of Fi can vary. As you see from the simple example, I mean, if you just take, sorry, so for this talk, I will try to use C star. The whole thing, I mean, yes, doesn't matter. It works over any field. So if you just use the standard action on AN inside Pn, then you have the two fixed point sets that are P0 and Pn minus 1. So they can be arbitrary, but they will play a key role in our thing. Right. So the basic, then let me do a very stupid example that tells you a bit about choosing these open subsets. So let's start out with, again, C star acting on P1 times P1, and you take one action to be trivial. Okay, the section here, and here you have the standard action. You just scale on the affine line. That's of course boring. So it looks. So I would picture this action like this. So I have just the constant line where nothing happens, and on the P1 I have the standard action. To make it a little bit more complicated, pick one of the fixed points and blow it up. So let's blow up the point 0. I never know how to. So let's blow up the point 0 of this P1 times P1. So then this action gets a little bit more interesting. Looks like this. You will have these two, you will have an exceptional divisor going. So this one of these P1s is broken now. And right. So, and here yes, I have to say two things. I mean, here you already see that you now have a choice on choosing open subsets that have a good moduli space. So here you can just, of course, if you choose the open part, you have a free action, you just get your P1 back. If here you remove all the fixed points, you get a quotient that is no longer separated because the generic orbits can specialize to two of these exceptional divisors. So you have to choose one of the two exceptional divisors. Well, either the exceptional divisor or the curve, the proper transform of your original curve. Once we remove one of them, you get a nice separated quotient. That's the key example to keep in mind. So now, what does this line bundle give you? So although these dimensions can vary, so here you can see they, even along flow lines, they can jump up and down. it gives a lot of structure on the relation of these, on the lines connecting these two components. So the ample line bundle gives structure to the closure relations of flow lines. And for me, there's a basic computation. So there's computation is the following. So if you, how did I want to write this? If you just let C star act on the projective line, so any closure of a flow line will be a P1. So if you just let this act on P1, then by some weight, this will be act with some weight, say L. And you have you have this flow line, you have your linearized line bundle, so you can pull it back. So then, this lifts. So all of these, one, say, maybe it's of -1 that I will write down. So you have lots of options to lift this. Stupid. So I can just, for example, I can take such a lift. But the point is that the degree, so if you have L linearized on P1, you get that this degree of L will just be the difference of the weight at the 0 point and the point at infinity divided by this, well, the weight of the action on the P1. It will be something like the weight at 0 of your L minus the weight at infinity of your L divided by this L action. So in particular, and for the weight, so I just mean you at the fixed point, you have an action on the fiber of this L. So this gives you a weight. And there's always a sign issue depending on whether you look at the geometric line bundle or the sheaf. Well, let's not get into it. It's confusing, but that's essentially what you do. So this is determined by the weights. And so this is sort of the algebraic geometry's replacement for a moment map, because it tells you that if I just have a GM action, I could attach the weight to any of these fixed point things, and then along flow lines, I know that the weight has to go down or has to go up in order for this to be positive, which it is if I have an ample line bundle. Yeah, so this, for example, in this situation, I mean, I could downstairs, I could just choose any ample bundle here, and I might have a weight 0, weight 1 there. Oh, sorry, maybe I should, for today, fix my conventions like this to make it positive. Now, if you pull it back, it's no longer ample. You have to correct with the ample stabilizer. And so you might get weight 0 on this fixed point component. Here you have the additional fixed point, and you might get weight 2 there. So that is how this works. And that's, yes. And so this is how, from this structure, you can deduce the ingredient for this conjecture. So what do Bielinski, Biruda, and Stromese do? They attach to this X comma L with the torus acting, they attach a cell complex. Let's call it cell of X comma L. And how is it defined? Well, for each, if you pick a point in X, you define the cell of X to be the set of all indices in your, so the set of all components that intersect the closure of the orbits, such that the ith 6-point component intersects the closure of the orbit. And the dimension of the cell is, well, it's the dimension of this torus orbit. So it's R minus the dimension of the stabilizer of your point. And you glue along. So you identify cells if they are equal, and glue along boundaries. So you just remember the cell. So if you have 2 points that have the same cell, then identify them. And you glue along orbits in closure. Yeah, so if I have a point in the orbit closure, it also has an orbit, and this will be a boundary cell of this. And now there's the generic orbit. This will give you what's called the basic cell. So there's one open subset where these closures are the fixed closure. So in this example, it just will be the 0-2 interval. And here we see that this is essentially the only cells we get is the 0-2 interval, the 0-1 and the 1-2, and these are glued together. And now I can probably already tell you what this conjecture was. Yeah, no, I should also tell you the next thing. If you have a specialization of orbits, that have the same dimension, then the specialization, this will give you, gives a subdivision, gives a partition of orbits, where this is the generic one, partition of the basic cell. Right, so if you start out with this orbit, you close it up to say this orbit. Well, if you take the honest closure and close it up, you will also find the other thing. And so this gives you a partition of this, of the interval 0-2 into the interval 0-1 and the interval 1-2. And now the conjecture is the following. Right, so for toric, yes, I should say this, that's very good. So for a toric variety, so you can, well, in general, maybe you can look at this as follows. So how do you think about this cell? Over the complex numbers, you can look at this orbit closure and just divide out by the S1 action. And this will be embedded into the character lattice of your torus. And this is just the real vector space, R to the R. And you just map the fixed points to the character that is given by the character on the line bundle. So this gives you so this will be the convex hull. So so this will correspond to the cell of X, and it's the convex hull of this of the characters given by the fixed point component and on your acting on the line bundle L. So if I take any point in the fixed point component, the line bundle L gives me a character of the fixed point group of the fixed point, which is the whole torus. So it gives me a character of the torus. And that's sort of in terms of moment maps, this is the moment polytope. And it's just the algebraized version of this. I don't need to talk about this cell, but it's where this comes from. Yeah. And then you probably and then in this case, situation, you will also know that if you have a specialization of orbits and you close it up, you just get a decomposition, a subdecomposition of the cell of this polytope. So now I will only state the conjecture for geometric quotients. As I said, there's also versions for good quotients and whatever. Conjecture is the following. So I can either say an open subset of this quotient stack or say an open T-invariant subsets admitting a proper geometric quotients. They correspond to what they call moment measures. So maps from your cells, from the top dimensional cells, to 0, 1, such that for all subdivisions of the basic cell, so I call this, I should have given it a name. Let's call it C basic. I is not a good name. It's J. There exists exactly one J such that M of J is equal to 1. So in our example, this is this toy example, this is what we see, right? The only special subdivisions of our basic cell that we see is the composition in these two intervals, and we have to pick one of the two intervals. And so that's the conjecture. And then how to get from here to there? Well, you'd say that a point is in this open subset if and only if, well, its corresponding cell is a cell that gets maps to 1. This is readable. So that's their conjecture. So I want to comment on this. So the first thing is that they noticed already that this is a sufficient condition is not so hard. Because essentially, I mean, you want to have, well, if you have a specialization of orbits, you want to have a proper quotient, you have to allow at least one of the possibility specializations of the torus to be in the quotient, otherwise there will be a hole in your quotient. You want it to be separated, so only one of the closure things can be allowed. And then once you have it, you can sort of check kind of by hand that gluing local quotients will give you a separated proper space. The question is that this is a necessary condition is to me surprising, And let me tell you why I find it surprising. And it's surprising for at least two reasons. For me, the first thing the first reason of this is that the set of points x and x such that the del of x is some fixed cell can be disconnected. So in kind of this picture, this could happen at several occasions that you subdivided your cell. And so then from this geometric picture, it's unclear why on different components of this set, you should be forced to make the same choice. Kind of unclear why this should be the case. So why do we need to choose the same same cells in different component? So why does the choice in one of these components to be inside of U or outside of U affect the choice at the other components? And the second thing that's weird is that because of this gluing thing, the subdivisions of the basic cell do not need to arise from specializations. And let me give you a toy picture of how I think of this. Right, you can have this kind of picture where you in the end find a decomposition of this interval into these four intervals. But on each orbit, there's only ever the choice of decomposing in 2 or maybe 3 of these intervals, and not all 4 of them. Right, so there's not one orbit specialization that would give you in the closure a chain of P1s passing through all the fixed point strata. So again, this moment measure tells you, well, you have to make one choice for this highest decomposition, and it's unclear why this should give you a choice in general. Okay, so I hope that this kind of motivates why I find this intriguing. And so we would have to think about how, so the question that arises is how would we get such a moment measure from the existence of a proper quotient? And I hope that I did the correct computation to tell you how this goes. Kind of simple idea. So, given U with proper quotient, how to find this moment measure. And I have a suggestion. So I look at this quotient stack, and okay, so somebody gave me an open substack that admits a geometric proper quotient. Okay, so let's see what this gives me on cohomology. And I will take rational coefficients. You will see why in a second. Probably already see. So I can restrict to the cohomology of the quotient stack. And because I assumed this to be a geometric quotient, rationally, this will be isomorphic to the cohomology of my quotient space. Now that's a proper variety. So if I look at the top dimension here, I will just find Q. So the top dimension here will be Q. So this will be, I will call this the top dimension, and I put it in quotation marks because this, if you don't like stacks, this will be the equivariant T-equivariant cohomology of X, which is infinite in infinite degrees. So this is not really a top dimension where this top is simply the dimension of X minus the rank of my torus, if I assume that the generic stabilizer is finite, which I can assume. Right, and I have to put a factor of 2 to accommodate for my complex numbers. And so now what does this buy me? Now if I pick a point T, X and X, I can look at its closure of its orbit. And this will give me a sub stack of this quotient. And this thing has an equivariant cycle class in here. So there's a cycle class in this thing. And this will map to 0 here. Well, if and only if, well, this closure doesn't, this thing doesn't intersect U, right? So it is, the question whether this cycle class goes to here or goes to 0 here or not is completely determined on whether X is in U or not. So this goes to 0, goes to something non-zero if and only if X is in U. So that's good. That looks something like this thing. But what on earth should it have to do with the cells? And that's also not hard, I claim. That's 5 minutes, right? And this is.
You started at 20.
I started at past, right? So it's
No, it's like later.
Yeah. We have that. If I space, if I do 5 minutes and then you can. So what's the point of how do I relate the cycle class to these cells? Well, I just compute what this cycle class is when I localize it to the fixed point. So there's a localization that tells me that this equivariant cohomology injects into the direct sum of these fixed points of the equivariant cohomology of the fixed points. And because they are all smooth, this is not really something difficult. It's the cohomology of, well, the same holds for X, by the way, times the cohomology of the classifying space of the torus, which is just a polynomial ring. And if you want to write it, it's really the symmetric algebra of your character letters. And so the claim is, if you let the multiplicity, so if you take X in X, and you take the with finite stabilizers in T, and you take the multiplicity of X to be the degree of the stabilizer, then if you take mx times the class of this quotient, maybe make this, call this the localization map. So if you localize this, so in this direct sum of the cohomologies, is determined, this compute can be is determined by the cell of X. And so this, and because under specialization, of course, cells, I mean, the cycle classes will go to the cycle class of the closure, you also get this decomposition for specializations again back from this segment. And so this is a funny local computation, and it's I think, and it's kind of not so hard. So if you want to compute what this localized class here is, so in the part that corresponds to the fixed point, you will just find the cycle class of a point in this. It's the only thing you can find. And so you're only interested in computing what is this thing, which is made out of these characters. But this is in the end reducing you to a computation where you just have to compute for a torus acting on some affine space, and you have some vector in this affine space such that the orbit closure contains 0. And you have to compute these classes. And so you will see that, so if you take a point here, you will decompose this affine space into eigenspaces for this T. And you will see that this class only depends on the convex cone spanned by these characters that you find where the coordinates are non-zero. And so why do these characters then determine for you the cell? Well, if I have to, this comes back to this basic observation that I had in the very beginning, and that's why I made it. So if you have a character flowing outside by some coordinate here flowing outside by some character, well, then the line bundle tells you with the degree on this thing along this character. So you can compute the character that you will find on this compute thing fj by knowing what it is on fi and on chi and the degree of the line bundle. And so that's why this character actually tells you what the character will be on the next component. So if you have two rays that have two different rays, they will give you different limits. And that's how you get back to the cell. And that's all I wanted to say. Thank you.
Any questions?
Thank you. So you started saying that with this, you detect quotients that you, by GAT, you wouldn't detect. And can you give us some examples of this in some of the moduli spaces that we like and love, and where you can detect this new sort of subsets or something?
Well, okay, let me. So for the moduli spaces you like and love, it's, I mean, like moduli space. So if you, for example, if you look at moduli of vector bundles on a curve, there the funny thing happens, and it's a theorem of Jochen and Dario, another PhD student in Essen, that the semi-stable part is the only part where you have a good moduli space that is actually a scheme. So there's a larger part where you have a good moduli space that is an algebraic space. which is not separated, but around the, I mean, for example, around all simple bundles, you can have such a quotient. But there, the quotient will be an algebraic space and not a scheme. And I don't know whether there exists and so there exists some open subsets of this thing that have a separated good moduli space that is not contained in the semi-stable locus. But I don't know of an example where you would have a proper such quotient. In rank 2, it doesn't happen, and in higher rank, Eugen doesn't know yet, right? So, but I would say it's not completely unlikely that in these moduli spaces of bundles, you find that the only proper quotient you can get is only the ones that you can get from GIT. However, if you would like go to higher dimensional varieties, then if you look at these moduli spaces of bundles for varieties that are not projective to start with, but only proper, then you will be in trouble finding moduli spaces, and our methods, well, you might be able to find such things. So for me, this was really a toy case to have at least some, I mean, so what's the upshot for this from my perspective? So from my perspective, the stability, my favorite slogan is that stability of a point is actually determined locally around the very unstable points. So usually in your definitions of stability, you take some flags or something, but what you're really doing is you do Hilbert-Mumford criterion. So you generate your flag into the associated graded and look at the weight at the associated graded point, which is a very unstable point. So choosing open subsets will hopefully always be determined by looking at the most unstable points and looking at the geometry locally around this. This is exactly what this does, because you do a computation locally around the fixed points, which are the most unstable points. So in the case where you don't have ample line bundles lying around, so a line bundle would be class in H2. But this thing, this moment map, well, if you look here, it seems to be a cohomological ingredient in a different cohomological degree. And this condition that you have a cycle class for points seems to be the most natural one to ask for if you want to have a proper quotient. So I believe, so if you would like, I mean, I have not started this yet, but if you look at varieties that are not projective but proper and look at their moduli spaces, then this kind of condition might be useful. And I think it's kind of intriguing to have stability conditions arising from cohomological degree that is not 2.
Very interesting. Thank you.